Good morning. It's August 3rd, and this is your daily brief in science. Here's everything you need to know. A six-step biosynthetic breakthrough redefines how toxic plant compounds could be produced in the lab. Researchers engineered tobacco and other hosts to make adenosine, a diterpenoid alkaloid, using 6 key enzymes and a nitrogen adding step, aiming for scalable, sustainable production for medical research. The study maps how the 6 enzymes assemble the molecule, with the DAS enzyme taking on an unexpected nitrogen addition that completes the toxin's core structure. Collaborators from Michigan State University and the Czech Academy of Sciences trace biosynthetic genes across plant tissues to reproduce wolfsbane and larkspur pathways in lab settings, seeking a conserved route across species. Across wolfsbane and larkspur, the team identifies a 6-step biosynthetic pathway with potential for pain relief, cancer treatment, and malaria therapies. The project aims to enable production in engineered hosts like yeast or tobacco to scale up testing of these compounds, bypassing limited natural yields. Key findings include that a nitrogen source comes from ethanolamine, not ethylamine as previously thought, verified by feeding experiments. Tobacco-based experiments reconstituted part of the pathway and produced adenosine, which shows anti-malaria activity, demonstrating feasibility without wild root harvesting. The broader goal is to map the full pathway to replicate aconitine and related alkaloids, while noting some steps remain predictive pending further validation. Despite millions of years of evolution, wolfsbane and larkspur share a conserved 6-step biosynthetic pathway, indicating a common mechanism across species. Researchers from UF Crocodocs are radio-tagging male Burmese pythons in the Everglades to map movement and locate nesting females, mating groups, and eggs, guiding removal efforts. Implanted transmitters in males help track them to large fertile females during breeding, directing removal teams toward key breeders. The program uses surgically implanted transmitters and trail cameras to reveal nests, including a notable 111 egg nest near the Everglades and Francis S. Taylor Wildlife Management Area. The goal is not complete eradication, but to reduce damage, protect native species, and support ecosystem recovery in the Everglades and adjacent areas. Nesting and movement data guide searches in remote, waterlogged areas and support native wildlife restoration by targeting invasive pythons. Findings inform where to search, especially in hard-to-reach marshes, and support early detection and habitat management to protect native wildlife. A new analysis from the Potsdam Institute for Climate Impact Research finds global warming has accelerated since around 2015, even after removing natural temperature fluctuations. The study, published in Geophysical Research Letters and reported by Science Daily, notes the long-term warming rate has risen to about 0.35 degrees Celsius per decade, up from under 0.2 degrees Celsius per decade in the period 1970 to 2015. Researchers used 5 global temperature datasets and 2 statistical methods to isolate the long-term signal from natural variability, and both methods show the acceleration with high statistical certainty. They adjusted for natural influences like El Niño, volcanic activity, and solar variability. Yet, the extreme warmth of 2023 and 2024 remained among the warmest on record. The analysis emphasizes that future warming largely depends on the trajectory of carbon dioxide emissions reductions, with faster cuts potentially slowing the trend. The study does not assign a single cause for the acceleration, but notes that warming can accelerate in climate models and appears consistent with modeled behavior. 2 approaches, quadratic trend analysis and a piecewise linear model, indicate the change began around 2013 to 2014 and became clear by 2015. It reports more than 98% statistical certainty of the acceleration across all datasets. If current warming rates persist, the 1.5 degrees Celsius Paris Agreement threshold could be exceeded before 2030, contingent on future fossil fuel emission reductions. Overall, the findings point to a faster-than-expected warming trajectory with implications for near-term climate targets and policy planning. A new study from Boston University, published in Science Advances, links Kelvin-Helmholtz waves to the loss of Mars's atmosphere by solar wind boundary instabilities. Using simultaneous observations from NASA's MAVEN and China's Tianwen-1 missions, researchers track changes in the solar wind and observe ion escape in Mars's upper atmosphere. The work suggests these waves are a central driver of atmospheric loss, not a uniform global effect. Large plasma clouds form in the upper atmosphere, with the escaping ion flow concentrated on one side, depending on the solar wind electric field direction. The study builds on multi-spacecraft data to connect upstream solar wind conditions with ion escape near Mars, enabling a direct causal connection. It reinforces that Mars, lacking a global magnetic field, experiences direct solar wind coupling to its upper atmosphere, facilitating loss to space. The findings point to Kelvin-Helmholtz waves as a key mechanism behind this non-uniform escape, as opposed to a homogeneous atmospheric outflow. The research sets the stage for future work with ESCAPADE and additional simulations to quantify how much these waves contribute to total atmospheric loss. Understanding this escape process helps explain Mars's transition from a thicker ancient atmosphere to its current dry, thin state. The results may also have implications for other unmagnetized planets and certain exoplanets, where solar wind interactions could drive atmospheric evolution. A Milky Way proton pevotron has been identified in LHA ASOJ 1912+1014U based on gamma rays above 0.1 PeV detected by LHA ASO and supported by FERMI-LAT and Chandra data. This places the source among Milky Way candidates for proton pevotrons and opens the door to systematic follow-up studies to uncover its accelerators and driving objects. Initially labeled a supernova remnant in 2024, its multi-wavelength analysis now clarifies it as a proton accelerator. Key collaborators include Naoto Nakahara, Hidetoshi Sano, Takeru Murase, Tomohiko Oka, and Hiramasa Suzuki, with participation from institutions across the US, France, Italy, Japan, Sweden, and more. The discovery was led by Hiroshima University and published in the Astrophysical Journal on July 16, 2026. Multi-wavelength data from FERMI-LAT, Forest/FUGIN, Chandra, Tibet, AS-GAMMA, and LHAASO underpinned the finding. By integrating radio, GV, TV, and X-ray observations, the researchers built a comprehensive model that supports the proton pevotron interpretation. The study highlights the value of a broad, multi-instrument approach, combining Tibet AS-GAMMA, LHAASO, FERMI-LAT, FUGIN, and Chandra to identify proton pevotrons and advance understanding of cosmic ray acceleration. The researchers anticipate many more proton pevotrons in the Milky Way and plan to examine additional candidates to determine their prevalence and characteristics. Distinguishing protons from electrons as gamma-ray producers is challenging, and the multi-instrument strategy was crucial in overcoming this hurdle. This has been your Daily Brief in Science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.